Take a look around. The screen you're watching this on right now, the sharpest tool in a surgeon's kit, the camera lens that cuts through glare, they all share a secret. And it's this invisible technology, you might even call it atomic painting, that literally makes our modern world possible.
So, have you ever stopped to wonder how that's even possible? I mean, what gives these things their almost magical abilities, right? How does a plain old piece of glass suddenly stop all glare, or a metal blade hold an edge that's just impossibly sharp?
Well, the answer is, it's kind of simple, but at the same time, it's mind-blowing. It all comes down to an invisible layer, a tiny coating so thin that we have to measure it in, well, in atoms. So, yeah, welcome to the world of thin films.
Okay, so let's dig in. What are these invisible layers? Because we're not talking about just any old coat of paint here. No way. These are more like meticulously engineered supercoats designed to completely transform the surface of an object.
All right, so what exactly is a thin film? To put it in perspective, get this. Imagine a layer so thin that if you stacked thousands of them on top of each other, the whole stack would still be thinner than one of your hairs. Seriously. We're talking about these microscopic layers of material that are put onto a surface. Scientists call that surface a substrate, and they're there to fundamentally change how it acts.
Okay, that's the what. Now for the how. How in the world do you apply a coat that's just a few atoms thick? I mean, you can't just grab a paintbrush, right? The process is way more precise. It's almost sci-fi. Think of it less like painting with a brush, and more like, well, like painting with individual atoms.
So the technique is called vapor deposition. And honestly, the best way to think about it is like the most precise form of spray painting you can imagine. What happens is, inside a vacuum chamber, they take a solid material and just poof, turn it into a vapor. And then those individual atoms or molecules just gently float down and settle onto the surface, building up a new layer, literally one atom at a time. But here's the really cool part. This isn't just some random cloud of atoms sticking to a surface. No. It's an incredibly orderly process, like a tiny construction project. The film doesn't just show up. It actually grows, kind of like a crystal, and it happens in 4 really distinct and super important stages.
Okay, so first up is nucleation. This is where the very first atoms land on the surface and they form these little stable starting points, kind of like seeds. Then comes island growth. More and more atoms show up and they start attaching to those seeds, growing them into these tiny separate islands. After that, we get coalescence. This is where the islands start getting so big they actually touch and merge together, forming this sort of connected web-like network. And then, for the grand finale, the last few gaps get filled in and bam, you have a solid, uniform, continuous film. It's this beautiful, bottom-up building process, all happening on a microscopic scale.
Now, what this all really points to is the incredible amount of control scientists have over this whole thing. I mean, to get the exact properties they want out of the film, they basically become, well, they become atomic chefs. They have to meticulously control every single ingredient to create the perfect recipe.
And one of the biggest ingredients in that recipe? Temperature. It's huge. See, if you do this at low temperatures, the atoms are kind of sluggish. They land and they pretty much just stick right where they are. That gives you a weaker, more porous film. But if you crank up the heat, now those atoms have energy. They can zip around on the surface a bit, find the absolute best spot to lock into place, and what you get is a film that's super dense, super strong, and perfectly structured.
And it's not just about the heat either. The scientists are in there fine-tuning everything. We're talking about the pressure inside the chamber, the speed of the vapor flow, even the energy of the atoms themselves. Every single one of those things is like a dial they can turn to get the final product just right.
But, you know, a perfect coating is totally useless if it just flakes right off, right? And that's a huge point. As researchers like Zhu, Wang, and Fang have highlighted, the surface you're coating, that substrate we talked about, is just as important as the coating itself. You have to prepare that surface perfectly because that's what creates the strong bond. That's what makes sure the whole thing is going to last.
Okay, so let's bring this full circle. Why does all this matter? Well, all of this crazy microscopic control, this atomic level cooking, if you will, that is what translates into the amazing real-world abilities that we can actually see and use.
Think about it. By controlling exactly how that film grows, you can design it to be incredibly hard and wear-resistant, perfect for something like an industrial grinding tool. Or you can make it chemically stable so it won't rust or corrode. Or you can get really fancy and fine-tune its optical properties to mess with light, creating those anti-glare lenses we mentioned. This is the magic, right here.
This is how we get from atoms to actual ability.
Okay, so you've got your perfect atomic recipe. But how do you know you actually got it right? How do you do quality control when your work is happening at a scale you can't even see? You can't just, eyeball it.
Well, to see the invisible, scientists use some seriously powerful tools. They have these incredible microscopes that can actually see the texture of the surface, right down to the individual atoms. They use things like X-rays to check and make sure all those atoms lined up in the perfect crystal structure they were aiming for. It's basically the ultimate form of quality control, making sure that atomic recipe came out exactly as planned. And that, right there, is the real power of all this. We've gone way beyond just finding materials out in the world. We are now actively designing them, literally atom by atom, to do exactly what we need them to do. And that just leaves us with this huge, fascinating question. If we can do this, what challenges are we going to solve next? Right? Are we talking about hyper-efficient solar cells, phone screens that are truly unbreakable, maybe even self-cleaning windows? The possibilities, well, they're pretty much as endless as our imagination.